the stuff that you're seeing behind the dusting layer. And because the dust is associated with the gas has structure on scales down to sub-parsec, you can have very, very rapid positional changes in what's going on with the dust, even though the underlying stellar distribution is quite smooth. So this complicates interpretations of CMDs, and this is actually sort of slowed down some of the star formation history work just because this is so complicated to deal with in terms of modeling it. But it's a really good way to study dust. So what I took on was starting to try to understand dust. Now, there is a rich literature, especially in the Milky Way. A lot of people here at Harvard, Elizabeth Goodman, Charlie Latta, Lombardi, there's a lot of people who have done a huge amount of work with extinction mapping in the Milky Way. This is something that's largely done in the near-infrared, done with 2MASS, and it's got lots of great features. So if you can map the extinction of dust, it gives you a pretty good probe of the total gas column density. So within a given region, if you're assuming that you're looking at something that has a relatively uniform dust-to-gas ratio, making a map of a molecular cloud is really telling you something about the total gas column density, whether it happens to be emitting CO or CO or whatnot. It also makes it a really nice complement of emission studies of the gas and of the dust. So you can say, how does the total column compare to where I actually do CO, do CCO, or where I actually see emissions from the dust. And within the Milky Way, these kinds of extinction maps have shown to have a really quantitative connection with star formation, that people have been able to identify that there's certain extinction thresholds that tend to be associated with the formation of molecules, with the formation of stars. So this background are maps of the Orion complex from Lombardi et al. 2011, but there's dozens upon dozens of excellent papers that can be cited about this. This is just illustrative. Okay, so on this particular plot, I just highlighted a couple of things in terms of color scale. So AV of 1 is sort of a very, very light beige. AV of 3 is kind of medium. AV of 5 is where it starts to get a little bit darker. Typically, this threshold of AV of 1 is about which molecular clouds go from being translucent to not, and you start seeing CO. Once you get well above an AV of 5, that's when you start to get some of these really dense gas traces that seem to be much more linearly related with star formation. So the other thing I just want you to note is that on this scale, I'm going to talk about 25 parsec scale regions in M31, and so I just want you to have some idea about what 25 parsecs might look like at a typical distance of Orion. Okay, the other thing that's known about these molecular cloud regions from studies that have been done in the Milky Way is that in general they have log normal distributions of extinction. So that if you take this whole region and you make a histogram of how many pixels there are at every possible extinction level, you wind up with something that looks like this. That it's a log normal with a well-behaved peak, and then a long tail towards high extinction. This is work by Junie Kainulainen, who also thinks that in general that there is also an excess you tend to find in the star-forming molecular cloud. So it's not a perfect log normal. In the ones that tend to have star formation, you maybe get a little bit of an excess. But in general, a log normal describes a large fraction of what that dust distribution looks like. So Junie actually gave me one of his maps, which I subdivided into sort of approximately 25 parsec scale regions, and then within each sub-region I plotted the histogram of all the pixel values, and you can see that in large numbers of these, a log normal is a pretty good representation. The log normal does start to break down when you look at these regions where you have kind of the highest contrast and filamentary stuff, and so you can kind of see maybe why you get this tail in regions where you start having these kind of caustics in your dust distribution. Okay, so the thing is that this log normal distribution of dust, modeling the background view of the stars, is probably what's going on in those color magnitude diagrams we're seeing in M31. And so we're going to now use that to try to infer what's going on with those distributions of resonance within M31. So what we do is we take regions on the scale of a brick. Through the magic of table function, we divide it up into 25 parsec regions. It's about almost 7 arcseconds on the side. And each one of those is probably sampling a region that would look like this in the Milky Way. That if we had infinite resolution and depth vision, we might see an extinction pattern that looks like this. This is the Taurus molecular cloud. So we don't actually see this. Instead, what happens is we measure the colors and the magnitudes of, in each region there's an order 80 to 100 stars that falls in a 25 parsec square box. And within this region, we measure the colors and magnitudes of all of these stars. And so these stars, what they're going to do is some fraction of them are going to be in front of the dust layer, and those are going to look like normal RGB stars. Some fraction of them are going to be behind, and those ones that are behind are going to be sampling this dust distribution. So this star that fell on this line of sight would be highly reddened. This star that fell on this line of sight wouldn't be reddened at all. And so we're not going to be able to say for sure which one star is associated with what, but we can analyze the distribution and learn something about what are the statistical properties of the dust within that 25 parsec box. We can't map it out as beautifully as done in the Milky Way, but we can infer some broad statistical properties. So for example, here is a Junie's map of the Orion Nebula. Here it is if you divide it into 25 parsec boxes, and then you step them by 12.5 parsecs, which is kind of nice with sample, the features, and then plot it again. And this is just the median within each grid. So within this box, what's the median AV that you get? And it makes this map. And you can see that it basically gets the broad structure that the highest extinction region is in here. There's a little bit of a shape to it. And that's if you take every single pixel in a grid box. But it turns out if you take only 25 per box, 25 samples per box, it's not going to get a lot of it. Like you maybe miss some of the very highest features on any one realization of it, but in general, with 25 samples, which is fewer than we actually have in most of our cases, you still do remarkably well with sampling the distribution. Yes, you're not going to be sensitive to some details of the tail, but in terms of what's the median AV in a 25 parsec box, we can get that. Okay, so operationally, what we're going to be doing is we're going to be modeling the color magnitude diagram like this. We're going to be modeling it with the sum of a red giant branch that's unreddened plus a red giant branch that samples some log normal distribution of reddening behind it. So the way this works is that within each 25 parsec pixel, we fit the color magnitude diagram. And so we fit it with 4 grams of the log normal. We fit to the median AV. We fit to the width of the log normal. And then we also fit to the fraction of stars that are in the reddened peak compared to the unreddened peak. This turns out to be really interesting again. So here's an example. So this is our model of the unreddened peak, of the unreddened RGB, and you can see that all the stars are redder than it. So if you actually build this model, this distribution is very well fit by a median reddening of about an AV of close to 2, a very characteristic width of the log normal of about 0.4, which is really typical of what people see in the Milky Way, and a reddening fraction where about 75% of the stars are in the reddened peak. To build these local models of the unwritten CMD, we do this empirically rather than fitting a functional form because the intrinsic CMD is really complex. So what we do is we, in bands of constant stellar density, which captures all our observational errors very well, and also is a nice proxy for radius, we then identify regions that have the narrowest RGB. We then also cross-correlate those with restrained published map based upon dust emission. So we also cross-correlate those and reject any point that also has significant dust emission. So we're just trying to find the cleanest, most dust-free things to use for our model. These are not a fair sampling of the galaxy, okay? And so we do have some slight population things, but I'll show that the population in the RGB is really very, it's pretty well behaved, so it's not as tragic as it might be. And I think we can do some advanced modeling things to fix it. So that, there's just certain regions of the galaxy where there happens to not be much dust, and these are they. These are what the resulting RGB in these low, in these, as close to zero stations we can get the regions look like as a function of surface density. So this is in the inner galaxy, moving outwards. You can see how the data gets fainter and fainter because we're doing better with that crowding limit. But it's very, very thin. It gets a little broader as you go here because the crowding adds additional photometric errors to things. The other thing I want you to know, the arrow shows you an AZ of 5. So we're quite sensitive in the near infrared to very, very, very large red rings. Okay, if there were an AZ of 10, you would probably couldn't see it, you didn't say much about it in the inner regions, but in the outer galaxy we definitely would be sensitive to it. The other thing I want you to note is the width of the RGB. It's very, very narrow intrinsically. It's limited by photometric errors in some regions, but in the uncrowded regions especially, it's incredibly narrow, which means that even a relatively modest amount of reddening is going to take it out of the main distribution and will be sensitive to it. However, it also sets the floor that this method is going to suck at low reddening because we're going to run into the limit with the width of the RGB is pretty low. Okay. You can look at the properties of the RGB. This is the color magnitude of just the main locus, so basically the ridge point of it. Where it's color-coded, this is the inner galaxy going to outer and outer galaxy. And you can see it's very, very smoothly changing, and it doesn't change by a whole lot. So this thing is having few sampled regions, properly interpolating over them isn't a bad match to try to figure out what the unwritten CMD is. Here's the width of the RGB as a function of magnitude. And so in the bright regions, the narrowest it gets is about 0.025, which as far as we can tell is about the limit of the photometric errors. So the intrinsic RGB in the infrared actually may be narrower than that. This is also why this method doesn't work very well in the optical, because the optical, there's a more natural spread in terms of AV. So of course, this arrow is about 0.25 AV. So generally, results at the level of 0.25, you just shouldn't really trust them because you're limited by the width. Okay, so here's what you get. So here's a map of the median AV roughly corresponding to this region over here. I don't know if you can see a little bit of kind of striping square structure just popping up in here. That actually turned out to be sort of 1.5% errors in the flat field between the two filters. So we were sensitive to, as I said, that we can really do a lot of stuff in calibration. But I think I can actually make this better by doing a better job on the WISC3 flat field because we're being sensitive to it. So this map is basically, it's 12.5 parsec sampling of 25 parsec native resolution. Here's a comparison to an optical image. And a lot of these very filamentary structures you see here, really they match one-to-one with what you actually see here. Now how does it compare with other dust tracers? This is the state-of-the-art dust map that Bruce Gray published. It's a lovely piece of work based upon modeling all the Spitzer and the Herschel and the 2-mass data for M31. And you can see that what we have is significantly more resolution. Things, all the features match beautifully, but the resolution that's available here is much, much better. I think the drain map is almost certainly better at very low extinctions for those reasons that I was saying that I think our technique is just really sensitive. So in the low emissions, I think this is superior. Sorry, at low AV, this is superior. I think the resolution gain, doing it this way, I think is incredibly useful. It also maps very nicely with the H1. This is another reason. So this is that outer star-forming ring. This is that 10 kiloparsec ring. Again, beautiful matches, faint little filaments popping out all over the place. This is really quite, I'm trying to sell some dynamicity on this. This is, the bulge is kind of right here. Look at these little spurs and filaments coming off here. This is something where dynamicists have known that gas does this. And this has a very clear wavelength dependence, a real clear spatial wavelength dependence. That presumably is telling you something about dynamical instabilities in the gas and the gaseous side. And they're much more tightly wound than in the simulations I've been able to find in this phenomenon. So I think there's something interesting there for some of the model. But I mean, they're just neat. So we have curve agreement with the dust morphology for emission, which is really amazing. And every single one of these pixels, well, every other one is done independently. Okay, and yet they are tracing exactly the same very large-scale structure here. I mean, just one to one. If you just look at, that has like a little hook right there. That's that little hook right there. I mean, that tails off that way. That tails off that way. Right? I mean, it really is a remarkable level of agreement, which I think is a tribute to both methodologies. The problem is that was a little bit of a cheat because I did not show the previous plots on the same scale. So in the mapping that Bruce does is that he builds a very complex model for the dust, calibrated off the stuff in the Milky Way. And then for that dust model, he can say, for this amount of emission, I would see this amount of extinction in AV. And so if I use that conversion, and Bruce and I have been in contact about this, the amount of AV that's inferred from his model is more than a factor of 2 times greater than what you actually see by looking at the actual reddening of individual stars. And there's not that much uncertainty. We haven't measured AV. What we've measured is reddening in 2-near infrared filters, but that conversion to AV is pretty stable. It doesn't, it's got 10 to 50% uncertainties in terms of variations in RV, so that's not factors of 2 and 3. So, further evidence that this offset isn't really, it's just not feasible. So this is the best fit model for a region. I think this is probably the one that we saw before. This is the probability distribution. So we do Monte Carlo fitting of the models in every single pixel. This is the model for the mean AV. There's nothing you can do that's all of a sudden going to say that I mistook 4 AV for actually being 2 AV. So it's not feasible. This is what it looks like if I just say I'm going to multiply the AV by roughly a factor of 2. It's just not consistent with the data. I can maybe get a change in the mean AV by just making it a very broad log normal. But again, I can't make it broad enough and have it be consistent with this, and it's also just a terrible fit for the data. So there really is something off with these emission models. It's a little bit worrisome because this is, the primary tool that has been widely used to interpret what's going on with dust masses and dust emission when dealing with the Thing survey or the Kingfish surveys. And those models there's clearly an issue with normalization. The relative stuff is beautiful. Normalization is off. And this is not the first time. There are the same tension as evidence in comparison with the Planck data. Other people have dust models that also